Welcome viewers to the third segment of the sixth lecture for the online series of lectures for the course of linear algebra. We are going to open the discussion of this segment with an example. Example 2. Let F be a subfield of C, the field of complex numbers, okay. It's an easy exercise for you to check that the following matrix, the following 3 times 3 matrix P given by this expression is invertible with inverse P inverse is equal to minus 1 to 11 over 8, 0, 1 half, 3 over 16, 0, 0, 1 over 8. Okay. Now using 13 prime, so let me write down 13 prime for you, which was the expression for the coordinate matrix of the vector u prime j relative to the basis b to be equal to this column vector given by p1j, p2j, all the way down to pnj, okay, where b is the ordered basis of R3, consisting of the standard basis elements 1 0 0, 0 1 0, and 0 0 1. Okay. Now, according to 13 prime, u prime 1, if I take the coordinate matrix of this vector relative to this standard basis of R3, then this is going to be the first column, right? The first column of the matrix P, which is minus 1 0 0. Now similarly, we can write down the coordinate matrix of the vector u2 prime relative to the standard basis B to be equal to the second column of the matrix P, which is 4 2 0. Now the coordinate matrix of the vector u3 prime with respect to the standard basis is the third column of the matrix P, which is 5 minus 3 8. Okay, this way we get the coordinate matrices of all of these elements of the ordered basis B prime. Okay. Okay, I need space. The three vectors mentioned a while ago, these three vectors, u1 prime, u2 prime, and u3 prime. Okay, so these three vectors constituting the basis, the ordered basis B prime, can be expressed by means of their coordinate matrices given by these expressions. Okay, and these three vectors form a basis of B prime of F3. Okay, all right. So we have two different bases, B and B prime of F3. One is the standard basis, another one is given by this these three vectors in R3. Sorry, in F3. Okay, where F is the subfield of the complex numbers, of the field C of the complex numbers. Okay, good. Now we know from earlier discussions in the previous segments that the column vector consisting of these three vectors, the three prime vectors, is equal to P transpose times the unprimed vectors, right? Good. So from which it follows that the unprimed vectors can be written in the following way: P inverse, the transpose of P inverse times the prime vectors. Okay, so now from this expression it follows that because we have the explicit expression of P inverse, I want I left it as an exercise for you to find that inverse u1, u2, u3, this column vector can be expressed as the multiplication of this matrix, which is the transpose of P inverse 11 over 8, 3 over 16, 1 over 8 times this vector, this column vector, u1 prime, u2 prime, u3 prime. Okay, good. So I can simplify it further, and which reduces to the following expression. This is minus u1 prime, and then we have 2 u1 prime plus 1/2 u2 prime. Okay, the third component is given by 11 over 8 u1 prime plus 3 over 16 u2 prime plus 1 over 8 u3 prime. Okay, therefore, so just plug in the values of the expressions of u1 prime. Remember that u1 prime is represented by the following vector. It is represented by the coordinate matrix of u1 prime relative to the standard basis B, which was this, right? Which was this vector minus 1, 0, 0, and u2 prime, the coordinate matrix of u2 prime relative to the standard basis was 4, 2, 0, and the coordinate matrix of u3 prime relative to the basis B was 5, minus 3, 8. Okay, so plugging in these expressions here for u1 prime, u2 prime, and u3 prime, we get the following expressions. So one immediately finds that u1 is minus u1 prime, which is just 1, 0, 0, and u2, which is 2 u1 prime, 2 times minus 1 0 0 plus 1/2 times u2 prime, which is 420. Okay, so I add these two vectors to have 0 here, then 1 here, and 0 as a third component. Okay, so now u3 is equal to 11 over 8 u1 prime, and u1 prime is going to be minus 1 0 0 plus 3 over 16 u2 prime, which is 420, and then we have 1 over 8 times u3 prime, which is 5 minus 3 8. Okay, well, this gives us minus 11 over 8, then plus 3 over 4 plus 5 over 8 as a first component, and the second component is given by 3 over 8, right, minus 3 over 8, and the final component is just 1. The third component is 1. Okay, so which reduces to the following vector. This is going to be 0. Okay, so this is just 6 over 8. Okay, so you add them up, you see that in the numerator you have 11 minus 11, which is 0, and this is 0, and the third component is 1. So it's the standard basis, right? B is the standard basis consisting of these three vectors, u1, u2, and u3. u1 is 0 1 0, u2 is no, u1 is 1 0 0, u2 is 0 1 0, and u3 is 0 0 1. Okay, so that we have checked that the standard base B is indeed the standard basis, right? And now the coordinates x1 prime, x2 prime, x3 prime of the vector u relative to the basis b prime, okay, are given by, you know the formula, right, from Theorem 3. x1 prime, x2 prime, x3 prime is equal to p inverse. P inverse is minus 1 to 11 over 8, then 0 1/2 3 over 16, then you have 0 0 1 over 8. That's P inverse times so this guy is the coordinate matrix of the vector u relative to the basis b prime. Okay, and this vector is going to be the coordinate matrix of the same vector u relative to the basis, the unprimed basis b. Okay, which we denote by x1, x2, and x3. Okay, good. So this is P inverse. So this is actually theorem, the second part of the second formula for the third theorem. Okay, good. Which reduces to this reduced expression of this vector, the coordinate matrix of u relative to the basis b prime, to be equal to, in terms of the coordinate matrix, the components of the coordinate matrix of u relative to the unprimed basis. minus x1 plus 2x2 plus 11 over 8 x3. Then we have half x1 plus 3 over 16 x2, and finally we have 1 over 8 x3. Okay, now we know that U can be written as a linear combination of the elements of the ordered basis, B. Okay. At the same time, U, the same vector U, can also be written as a linear combination of the basis elements of the ordered basis B prime. Okay, let's do this. So U can be written as x1 U1 vector U1 plus x2 vector U2 plus x3 vector U3, and it is also written as x1 prime U1 prime in the prime coordinates, x2 prime U2 prime plus x3 prime U3 prime. Okay, and now choose for example x1 to be equal to 3, x2 to be equal to 2, and x3 to be equal to minus 8. Okay, let me number this equation by 19, and this equation by 20, and this equation by 18. Okay, now if we plug in these values here in 18, we get the values for x1 prime, x2 prime, and x3 prime, which are as follows. x1 prime becomes minus 10, so we plug in the value of x1 here, which is 3, x2 is 2, and x3 is minus 8, and then you get x1 prime to be minus 10. Okay, and similarly you get x2 prime to be equal to minus 1 half, and x3 prime to be equal to minus 1. This is our equation number 21. Okay, I need a bit of space. Okay, since U1, U2, U3 equal to B is the standard basis of F3. Okay, so I think in some places I have been saying that it's the standard basis of R3. Okay, but I should have said it's the standard basis of F3 because we are considering a subfield of a complex number, which is not necessarily the subfield R of real numbers. It can be any other subfield. Okay, since this is the standard basis, so plugging in the values of x1, x2, x3, and x1 prime, x2 prime, and x3 prime in 19, we get, you see that 19 reads x1, so x1 is 3 times u1 is the standard basis 100 plus 2 times 010, and then minus 8 times u3, which is 001. Okay, and this guy is equal to, what is x1 prime? X1 prime is minus 10 times u1 prime then plug in x2 prime to be negative 1/2 in 19, and this gives us negative 1/2 u2 prime, right? u2 prime, and then we have minus 1 u3 prime, minus 1 times u3 prime. Okay, so we end up with 3, 2, minus 8. This vector is equal to minus 10 times u1 prime minus 1/2 times u2 prime minus u3 prime. Okay, good. At this stage, I again suggest some exercises for you from the book by Hoffman and Kunz. Suggested exercises. Hoffman and Kunz. Page 54. Okay. Problem number 1, 2, 4, 5, and 6. Okay. So there are 5 problems again. You should try to solve these problems. Okay. Now, we'll be discussing row equivalence, so it's revisiting row equivalence. We discussed row equivalence when we were dealing with systems of linear equations. Now, in the context of vector space, we are revisiting it. Recall that if A is an n times n matrix over the field F, okay, the row vectors of A, vectors of this matrix A, are the vectors. Okay, how many vectors are there? There are m row vectors, right? Because the size of the matrix is m times 1. We denote them by alpha 1, alpha 2, all the way up to alpha m. Okay, each of which is an n tuple. Again, why? Because the size of the matrix is m times n. So each of these vectors is in f to the n, right? That is, each of these m vectors is an n tuple. Okay, so in general, I write alpha I, the vector alpha I, as ai1, ai2, all the way up to ain. This is an n tuple. In fact, it's the ith row of the matrix A. Okay. Now, the row space of this n times n matrix A is defined to be the subspace of f to the n spanned by these m rows, m row vectors of the matrix A, spanned by these m vectors. Okay. So it's going to be a subspace of this vector space f to the n, okay, spanned by these m vectors, like I have said. And since it's a subspace of this finite dimensional vector space f to the n, it has a finite dimension. The dimension of that subspace is called the row rank of A. Okay, so let me write it. The row rank of the m times n matrix A is the dimension of the row space of A, which is the subspace spanned by these m vectors. Okay. Now, okay, let me erase everything. If P is a K times M matrix, okay, and we know from the discussions that we had earlier that A is an M times N matrix, okay. The size of A is M times N, okay, and we take this K times M matrix P, okay, then B, which is equal to the product of these two matrices, P and A, has size K times N, okay. So the size of this guy is K times N. So we denote the the rows of B by beta i's, okay. So how many rows are there? There are k rows, so we denote them by beta 1, beta 2, all the way up to beta k, okay. These are row vectors. And we had this discussion while we were studying matrix multiplication, right? That we can interpret matrix multiplication as a linear combination of the rows of the later matrix, okay. So it means that the rows of the matrix B can be written as a, so each row of this matrix B can be written as a linear combination of the rows of this later matrix, of this latter matrix A, okay. So where in the linear combination the coefficients are going to be entries of this former matrix P, okay. So let me write it for you. So we can write the rows of this matrix B as linear combinations of the rows of A, which we denote by alpha j's, okay. J runs from 1 to what's the size of A is size of A is m times n, so J runs from 1 to m, and the coefficients are P, I, J, okay. And here I is between 1 and k. Okay, this is equation number 22. Good. So each row of B can be written as a linear combination of the rows of the matrix A, the letter matrix A. Okay, it means that the row space of B is a subspace of the row space of A. It immediately tells you that the row space of B is a subspace of the row space of A. Okay, this is one important observation. Now take the special case where K is equal to M and P is an invertible M times M matrix. P is an invertible M times M matrix. Okay, so when we have this special case, then there exists an analog of equation 22 where each of the alpha i's can be expressed as a linear combination of the rows of B, that is BJ's. The rows of B, that is beta J's. Okay, so each alpha I can be written as a linear combination of the rows of B, which are beta J's, and in each linear combination, the coefficients are entries from P inverse. Okay, so so in this situation, we see that the row space of A is a subspace of the row space of B. Okay, all right, so which means that if the row space of B is a subspace of the row space of A, and the row space of A in turn is a subspace of the row space of B, we immediately see that they are the same. The row space of A is the same as the row space of B. Okay, so whenever we have this thing occurring, B equal to P times where A, where B is an M times N matrix, so is A, and P is an invertible M times M matrix, we say that in this case we say that B is row equivalent to A, right? B is row equivalent to A, and it will in turn mean that the row space of A is the same as the row space of B. So one therefore have the following theorem. Let me state this theorem. We just proved this theorem. Theorem 4, which tells us that row equivalent matrices have the same row space. Okay. In fact, we can strengthen this theorem, or we can improve this theorem by stating that if we have two matrices having the same row space, they will also be row equivalent. Okay, it's the other direction that actually holds, and which the proof is not that straightforward as this one, which will be stated as a corollary to this theorem. Which will be a corollary to the next theorem, theorem 5. Okay, good. So now, therefore, we see that studying the row space of a given matrix is equivalent to studying the row reduced echelon matrix, the corresponding row reduced. So studying the row space of a given matrix is equivalent to studying the row space of the corresponding row reduced echelon matrix. Okay, that simplifies the task. We don't have to deal with that given matrix. We can deal with the row space of the corresponding row reduced echelon matrix. Okay. Therefore, we see that studying the row space of a given matrix A is equivalent to studying the row space of the row reduced echelon matrix which is row equivalent to A. Row equivalent to A. Okay. So now it turns out that we need to study row space of a row reduced echelon matrix, and that we do by means of the following theorem. Okay, Theorem 5, which talks about how to study the row space of a row reduced echelon matrix. Let R be a non-zero row reduced echelon matrix, meaning that there will be at least one non-zero row in this row reduced echelon matrix. Okay. Then the non-zero row vectors of R form a basis for the row space of R. Okay. So if we are given a matrix, an m times n matrix, we can find the corresponding row reduced echelon matrix, meaning that the row reduced echelon matrix that we end up with is row equivalent to the original matrix A. So we take the non-zero rows of this row reduced echelon matrix, and those non-zero rows actually form the basis of the row space of the matrix A. Okay. Okay, so this was theorem 5. Then we have a corollary 1 to this theorem. Each m times n matrix A is row equivalent to one and only one row reduced echelon matrix. Okay, So given a matrix A, an M times N matrix A, you cannot find two row reduced echelon matrices, two different row reduced echelon matrices, which are both row equivalent to the given matrix A. You can never do that. Okay. Now the second corollary to this theorem 5, let me erase everything. Corollary 2 of theorem 5. Let A and B be M times N matrices over the field F okay. Then A is row equivalent to B if and only if. Okay, it's a stronger statement than we had in theorem 4. Okay, it contains both the directions, like we said before. If and only if they have the same row space. They have the same row space. Okay, this is corollary 2. So I leave it as an exercise for you. You can look up in the book by Hoffman and Kunz for the proof. To summarize, let me summarize what we have studied so far in this segment. If A and B are M times N matrices over F, then the following statements are equivalent. Okay. The first statement is that A and B are row equivalent. Equivalent. The second statement is that A and B have the same row space. So the equivalence of the first two statements is a consequence of corollary 2 to theorem 5. Okay, and the third statement tells us that B is equal to P times A, where P is an invertible M times M matrix, where P is an invertible M times M matrix. Okay. These three statements are equivalent. Good. Now, we move to computations concerning subspaces. Okay. So our next topic is going to be computations. Computations relating subspaces. Okay. First, I will describe the general method to do that, to do these computations. Then I'll show you by means of example how to do that. Okay. Suppose we are given m vectors in f to the n. So that's the starting point. We are given m vectors alpha 1, alpha 2, all the way up to alpha m in f to the n. In other words, each of these m vectors is an n tuple. So we consider the following questions. Okay, so the first question being, how does one determine if these m vectors alpha 1, alpha 2, all the way up to alpha m are linearly independent? Okay, that's the first question. More generally, how does one find the dimension of the subspace, dimension of the subspace W spanned by these vectors? Okay, so in the case when all these m vectors are not linearly independent, I mean that if we call it a set, a subset of the vector space, the subset consisting of these m vectors, if this set is not a linearly independent set, we can still ask the question, what is the dimension of the subspace spanned by these vectors? Okay, so more generally that will be the question. Okay, even in the case when these vectors are not linearly independent. Okay, all right, so now the second question is, given a vector beta in f to the n, that is beta is an n tuple, how does one determine if beta is a linear combination of alpha 1, alpha 2, all the way up to alpha m? That is, if beta if beta lies in the subspace W, if beta is in the subspace W spanned by these m vectors alpha 1, alpha 2, all the way up to alpha m. Okay, so this is the second question. The third question will appear to be a little vague at this moment, but as we discuss on, it will be clear to you. How can one give an explicit description of the subspace W. Okay, what we really mean by this explicit description will be clear in a while. Okay, so so these are the three questions. Okay, so let us discuss the most general method to address these questions. Okay, so we started with M vectors. Okay, M vectors in F to the N. Okay, let A be the M times N matrix with row vectors alpha 1, alpha 2, all the way up to alpha M. Okay, so we construct an M times N matrix where the rows of the matrix will be these M vectors. Okay, that is, the vector alpha I is going to be AI1, AI2, all the way up to AIN. Okay, this is an n tuple. Now perform a sequence of elementary row operations EROs on this given matrix A, given M times N matrix A, to obtain a row reduced echelon matrix R. That's the first thing to do, to obtain a row reduced echelon matrix R. Okay. At this point, the dimension of W, the dimension of W, right, which is defined to be the subspace spanned by these M vectors. Okay, it's a subspace of F to the N spanned by these M vectors. So at this point, the dimension of W, which is called the row space of A, right? The row space of A is simply the number of non-zero rows in R. Number of non-zero rows of R. Okay, good. So if row 1, row 2, all the way up to row R are these non-zero rows of R, then beta equal to row 1, row 2, all the way up to row R is the basis for W. Okay, this way we find a basis for the subspace of f to the n spanned by the m vectors alpha 1, alpha 2 all the way up to alpha m. The subspace W consists of all vectors of the following form. Beta is equal to sum over all expressions of the form Ci rho I, where the sum runs over I from 1 to 4. So the values of I run from 1 to R. Okay, these are the non-zero row vectors of R. Okay, so we take all possible linear combinations of the non-zero rows of R, and that way we get beta, a general element of the subspace W. Okay, and we see that these row i's are nothing but the ith row of the row reduced rational matrix R, right? Ri1, Ri2, all the way up to Rin. So we can take these Ci's inside the Ci multiplied with these scalars, and then summing over the i's. Okay, so now this is the n tuple that we have finally, sum over all i's of the expressions like Ci Ri1. This is the first component. The second component is the sum of all expressions like Ci Ri2, where I runs from 1 to R. That's the second component, all the way up to the nth component, which is going to be sum of all the expressions of the form Ci Rin, where I runs from 1 to R. Okay, and this is, so we call it the n tuple, b1 b2 all the way up to bn, and this is an n tuple, right? This belongs to f to the n. This is the ith row of R, ith row of R. Good. So b1 b2 all the way up to bn. So this is the coordinate of the vector beta relative to the basis beta. So relative to so I should have written it as calligraphic B. Okay, this is the basis that we are dealing with. Okay, now the coordinates b1 b2 all the way up to bn of such a vector beta, of such a vector beta, are then beta j is equal to the sum over all these expressions, sum of all such expressions like Ci, Ri, J, where I runs from 1 to R. R is the number of non-zero rows in the row reduced echelon matrix R, big R. Okay. So in the component form, beta is written as B1, B2 all the way up to Bn. Okay. So this expression of B is numbered as 23. Okay. All right. So let me erase these writing. Now so I think it's better to erase everything because I need space. So I'm going to write down the matrix R, the most general form of this matrix R. So this is R. So this is going to be the matrix. So suppose the first row begins with some zeros, okay, following which there is that and the leading one, and then we have some unknown numbers. Okay, they can be anything. Okay, now in the second row, the leading one occurs much later. So suppose it occurs here. So let me call this column K1. So if the leading one occurs, the leading one occurring in the second row occurs in the column K2, then K2 must be greater than K1, right? Suppose this is K2 where this leading one occurs. This is K2. And you know, so in the column where the leading one occurs, everything else is supposed to be 0. All right, that's the property, that's one of the properties of a row reduced echelon matrix. So it has to be 0 now. Okay, so now this was row 2. Then we have some unknown entries again. They can be anything. So now I have some so there are these rows, third row, fourth row, and so on. Then we have this generic row, we call it row J. Okay, so this is row 1, this is row 2. Now we are taking row J where the leading one occurs in the column Kj. So this is 0. Then we have 0 here. We have 0 here. 0, 0, 0, 0, 0. Suppose the leading one occurs here. This is Kj. Okay. Following which there's unknown numbers. Okay. Now finally the rth row, which is the last non-zero row, and so there all these entries are 0, 0, 0, 0, 0, 0, 0, 0, 0, and this is 0, this is 0. And finally there is something, so there occurs this 1 in the kth column. Okay, so again there are many rows in between j and row r, and so this is 1, this is going to be 0, and this is also going to be 0. Here this is going to be 0, this is, so it's the column containing leading 1, right? So everything else is 0 in such a column. Okay, so now there are these unknown entries. Okay, these unknown entries here. Okay, and everything after the rth row is 0. So these are all zeros. These are 0 rows. Gathered at the bottom of the matrix. These are all 0 rows. Okay, good. So this is the this is how this row reduced echelon matrix looks like. So there are such non-zero rows starting with leading 1, okay, okay. Now if the first non-zero coordinate zero coordinate, that is the leading 1, right? Leading 1 of the row y is occurring in the kth column of the row reduced echelon matrix R, then for all I less than or equal to R, okay, which means that I can be any of the first R rows, any of the first R rows. Then there are these 3 properties satisfied by this row reduced echelon matrix. Rij is equal to 0 if j is less than ki, okay. So in the ith row before the kith column, everything is 0. Okay, suppose we are taking k2, right? It's the second column. So this is the leading one. So everything before this leading one is 0. That's what A tells us. Okay, and then Ri kj is equal to delta ij. All right. So whenever I is equal to j, then this is equal to 1, meaning that Ri ki is equal to 1. Elsewhere it's 0. Suppose for the first row, this entry is going to be R1 K1, right? That is why it's 1. Similarly here, what is this entry? This entry is R J K sub j, which is also equal to 1. This entry is R, okay, R R K sub R, and which is also 1 because these R and this R are the same. Okay, good. Now, the third property tells us that K1 is less than K2 is less than all the way up to less than KR. Okay. Now, given these properties, now get back to equation 23. Which was, so it's the expression of the BJ's, right? Which tells us that BJ is equal to sum of all the expressions Ci Rij, where I runs from 1 to smaller. Okay, R is the number of non-zero rows of the row reduced echelon matrix. Now here take J to be equal to K sub S for some S less than or equal to R. In this equation, so that we end up with, so we just replace J with K sub S. So B sub K sub S is equal to here the sum is run over all i's, I running from 1 to R, and this is Ci and this is Ri, and J is K sub S. Okay, so the only contribution for such Rik sub S comes when I is equal to S, and that's 1. Elsewhere it's 0. So this is going to be just C sub K sub S, right? No, sorry. Right, Y. So when I is S, this is 1, right? This guy is 1. So this is just C sub S. Okay. So when I is S, this is 1. That's the only contribution. Elsewhere it's 0. So C sub S multiplied with 1 is just C sub S. This is equation number 24. Therefore, this equation 23 takes the following form. 23 takes the form B sub j is equal to sum over all i's, and since C sub s is B sub k sub s, then Ci is B sub ki, right? And what we have here is Rij. Rij. This is the explicit form that we talked about in the beginning. Explicit description, sorry. Okay, so here J is 1, 2, all the way up to n. This is equation number 25. Okay, so I can erase this this form of the row-reduced rational matrix, this long form. So the goal was to reach equation 25 actually. 25 is the explicit description that we mentioned in the beginning. In the third point, while in the third question, okay, this is the explicit, 25 is the explicit description of the subspace W spanned by these m vectors alpha 1, alpha 2, all the way up to alpha m, these m vectors. That is, let me explain, the subspace W consists of all vectors beta in f to the n whose coordinates, remember that beta was this n tuple, b1, b2, all the way up to bn, okay, with relative to the basis b that we described earlier. B consists of the basis consists of those non-zero rows of the row reduced rational matrix R, which we denoted by row 1, row 2, all the way up to row R. Okay, so with respect to this basis, the coordinates of this vector beta are given by b's, small b's, and the expression for the small b's are given by 25, equation number 25. Okay, so hence beta is equal to sum over Ci rho I, where I runs from 1 to R, and this in turn is written as, we know that Ci's are B sub Ki, right? We have seen here. So Ci is B sub Ki, and then we have rho I. This is how we find this vector beta, where I runs from 1 to R. So equation 26 is this explicit expression of such a vector beta contained in the subspace W, which is spanned by these m vectors alpha 1, alpha 2, all the way up to alpha m. Okay, so I think it's better to take a break at this point. In the last segment, we'll be discussing an example which describes this method, where in which example we will be applying this general method that we have discussed so far. Thank you for attending this third segment.